Hello, everybody, and welcome to yet another episode of Undercooled, a materials education podcast. We were asking what episode we're on, and it's beyond the numbers that I know how to count, so that's why we didn't say the number today. But instead of numbers, we have a person with us, Professor John Allison from the University of Michigan. So, John, welcome to the show. Thank you for being here with us.
Thank you. It's nice to be here.
We'd love to talk to you about all things materials education, maybe a little bit about engine blocks, wherever the conversation goes. But before we talk about engine blocks, tell us about yourself. Who is John Allison?
Who is John Allison? Oh, that's a question.
The existential question.
Well, I'm a husband to my wife, Julia, my lovely wife, Julia. A father to my wonderful son, JR, who lives in Lansing. My siblings and so forth, so I've got a family of people that I care about deeply. Let's see, I'm a public servant, so I've been an elected official in Ann Arbor Township, a trustee since 1996, and maybe more appropriate for today, I'm a metallurgist.
All things that matter. Well, since you brought up metallurgy, I'm very curious about the township role as well. Maybe we'll come back to that if there is time. Was metals the thing that called you into this whole field of study in the first place? How did you get started in material science?
Yeah, absolutely. So when I was in high school, I was interested in, science and math. I thought that was cool. And somehow I found myself at the Air Force Academy as a cadet. And my freshman year, they had a survey course in engineering mechanics. We were trying to pick majors. There wasn't a major in material science and engineering, but I didn't even know what that was. And as part of that course, we took a hunk of steel, 1020 steel, and etched it and looked at it under a microscope. And I thought, well, this is cool. All these little squiggly lines, phases of perlite. I thought that was interesting. And they said, now you heat it up and it changes. I said, well, that's even more interesting. And then they said, then measure the hardness. And that was interesting that it changed. And so that became a lifelong fascination with microstructure and how it affects properties to this day.
That's awesome. So you said you just happened to find yourself at the Air Force Academy. Why did you go to the Air Force Academy?
Did you just walk in one day and they kept you?
No, I grew up in a real small town in Missouri, Marceline, Missouri, boyhood home of Walt Disney. And I was probably going to go where my dad went, at Westminster College. And a guidance counselor said, he'd been to this trip to the Air Force Academy and he thought it'd be a place I might be interested in, had really good engineering. And so I said, okay, I'll apply. And so I went through my congressman and got appointed, and the rest was history.
That's awesome. So did you want to fly?
I didn't know. That was not the main thing. I don't know exactly what it was. That was many, many decades ago.
But then after you graduated, you clearly had to do your service to the Air Force. Where did you do your service?
At Wright-Patterson Air Force Base at the Air Force Materials Lab. So I was a graduate student in the BS. I took a minor in materials because that's all they had. But I took every course, loved it, especially physical metallurgy. But yeah. And so stationed at Wright-Pat. So we had, before I get to that, when I was between my junior and senior year, we had to do rotations, summer rotations. And so I selected one at Wright-Pat at the Air Force Materials Lab. So I did a junior, senior intern during the summer and just knew that this was exactly what I wanted to do. So then I applied to be stationed there and got what I asked for. So it was great.
That's fantastic. Now I guess we have to talk about the dark side. What did you do after the Air Force Lab? You got a PhD.
Oh, okay. So yes. So while I was a Wright Pat, I got a master's in metallurgical engineering from the Ohio State University. Sorry. I didn't know. I didn't understand. When as I was finishing, we did some career counseling type workshops and stuff, and it was destined that I would either be a forestry agent or a metallurgist. And so it said, you should go back and get further studies. And that sort of led me to a PhD. Yeah.
That's great. Who did you do your PhD with?
Jim Williams.
Oh, really?
Yeah, a notable titanium metallurgist.
Yeah. Who ended up being the dean.
So he was on the
Ohio
fact
State.
he was dean at Carnegie Mellon while I was there, and then he became dean at Ohio State later, some years later.
That's great.
You know, the Air Force connection is interesting because I grew up in an Air Force family, and I lived at Wright Pat for a few years when I was this big. But it was the same thing of, well, they have the school there, and they have Dayton University, and they have AFIT, and so, you know, all of these institutions, there's an incredible technological infrastructure in Dayton that I think a lot of people aren't aware exists, but there's a lot of innovation that happens there. So it'd be interesting to think if maybe we were in the same place at the same time at one point and never even knew it.
Probably, yeah.
So you finished grad school and you graduated.
Yep.
Did you ever consider not getting a real job and staying in academia, or did you hear your calling elsewhere? How did that turn out?
Well, so went back to get the PhD, and then I had the opportunity to do a postdoc in Europe. So I went for an industrial firm there, Brown Boveri Corporation, for a year, and enjoyed that immensely, the industrial research. And so when I finished that, I knew that I wanted to be in industry. And so I applied for a bunch of spots around the country, and Ford came calling, and so that was the one that I chose, and they chose me, and so, yeah.
Something that a lot of students ask around here, they've maybe gotten a job offer and they're getting ready to start work, and they're thinking, what am I going to do? Not just in the life sense, but what is my first project going to look like? How do I get started at a new company? So what was that experience like for you of having a first project? Were you responsible for something right away? Did they ease you into it? How did that go?
So sort of two answers to that. So one, the answer, so the first job was really Brown Boveri Corporation as a postdoc, essentially. And there it was pretty directed. So they knew they had this alloy they were developing, and they said, we want these studies of heat treatment to go out and figure out how to do that. So I did that. Then when I got to Ford, it was a much more open-ended. So I started just looking, talk to colleagues, and I knew that I wanted to do some work in fatigue as a carryover from my PhD thesis. So they said, sure, why not? Because it was, in those days, very fundamental lab. It was like the Bell Labs of the auto industry. And so it was pretty much self-directed, just like you might imagine. So I did that for a while, but then also I really was motivated to want to get parts on cars. That was always something that I wanted to do. So I started working on titanium valves and metal matrix composite connecting rods and all sorts of exotic metals. So I sort of split my career at Ford into two things. So that was that phase. And then I was really frustrated because it was very difficult to get those parts on cars. And so I started looking at something that was really pressing, and aluminum castings in powertrain were a big deal then, and we didn't quite know everything we needed to know. And so I started meeting some folks in product development and manufacturing and understood there was a lot we didn't know, so I took that on as a research project. And that became the sort of second part of my career.
So that was the virtual aluminum foundry.
Virtual aluminum castings. It became that eventually, yeah.
Wow. So you had risen up pretty high before you did that, because you were already, when I got here, you were already an adjunct faculty member.
Yeah.
And you and Wayne were doing an awful lot of work together.
Oh, yeah.
And even when Teresa got here, you were working with both of them.
Yeah. Yeah.
And so you were advising students,
Yep.
and I think Paul Krajewski was one of Wayne's
was.
students, but you were the co-advisor.
I was a co-advisor.
Right.
Several of us, yeah. Several of them. Yeah, Paul was
We're going to get
notable.
Paul on our
Good.
podcast because I have to ask him why Chevy pickup trucks are all rusting.
That's a good question for Paul.
Yes. But when I first heard you talk about the virtual aluminum casting project, I think it was at a ASM lunch or something, at dinner at one of those weird places.
Oh, sure. It was the, what is that? Yeah, they've got a lecture that, I remember that. Yeah.
And I was very impressed that you were able to convince Ford management to hire ab initio physicists, people like Chris Wolverton,
Yeah.
and to calculate interatomic potentials. Can you tell us a little bit about what that was like? What were you promising to Ford management, and what did they actually do for you?
Yeah. So that's an interesting aspect of the story. So at that time, Ford, as I said, was sort of Bell Labs. And so we had this physics department that had a lot of theorists. Very proud of that. They had a lot of theorists. And they brought Chris Wolverton through, who I didn't know. And I heard him give this talk on DFT, statistical mechanics for clustering, GP zone formation in aluminum copper. And I said, wow. You can actually predict that stuff. That's cool. And I told the manager of the physics department, we have to have him because we're working on this aluminum casting stuff and I can just see where that might fit. And so, yeah. Nowadays, they don't do as much in that sort of theory part, which is unfortunate, but that's kind of the way industry kind of goes sometimes. So,
Of course, Chris went to Northwestern
yeah,
and has had a phenomenal career.
Yeah, it was a sad day when he left, but it was good for his career. Yeah.
Right. So, what I remember from your talk way back when, before you started this project, they really just had like abacus or other finite element techniques. They viewed materials as a continuum, and they could calculate heat transfer. They could get the stress distribution, assuming it was a continuum. And if it was a liquid, they could do fluid flow. And that was it.
Yep, pretty much.
And so what did you add in that first version? Can you tell us a little bit about, you did solidification when you poured a molten aluminum into a mold. You were trying to design the mold so the end result, the engine block, was as perfect as possible. Did I get that right?
Yeah, pretty much.
And so what did you do? How did you make, because they couldn't do that before.
Yeah, so let's see. How can I start this? So I was working on fatigue. That was a big part of it. And one of the critical things we discovered as we went through this, so we were developing databases of fatigue as a function of solidification, heat treatment, what have you, casting practices. And the idea was to give our customers in the divisions who were going to use this data for design, that data and SN curves, fatigue life curves for that. And somebody said, well, can you predict that a priori? And I said, well, I don't think so. Because we'd have to know all this stuff about solidification, the phases form, and there are just too many variables. It's just too many variables. And they said, well, can you try? And I said, sure, we're in research. That's a reason for us being here. So I had another colleague who I'd hired, and she said, well, we could probably do this and this and this to predict porosity. And so that was the key driving force for fatigue, was being able to do that. I said, oh, that's cool. And so we began to pursue that, and eventually, cracked the nut on how to predict that, which was critical. Then I knew how to predict fatigue once I knew that.
Okay.
And so, that was one of many properties.
Porosity were nucleation sites for cracks.
Exactly.
So if you knew the size and the distribution of sizes and the density, you could make a stab at doing that.
Exactly. Yeah.
But you ended up doing much more than that for the virtual aluminum.
Oh yeah. So we
casting.
had heat treatment effects on properties, high cycle fatigue, strength, low cycle fatigue. Property known as thermal growth. So the precipitates that form also can lead to swelling, sort of dimensional instabilities. Yeah. Oh, and residual stresses. That was a big part of it, predicting residual stresses due to quenching or cooling during solidification and quenching from the solution treatment process.
Right. Because that's complicated. You pour this stuff in a mold and it kind of fills, but not exactly uniformly.
Right.
And it starts to cool depending on the thickness of each section differently. And then, of course, you design the mold to have other features that retard the heat flow, or you can heat things to increase it. So you were able to eventually predict all of those things.
Yeah. And so it's interesting. Before that, the durability calculations were all using sort of nominal properties, average properties. We knew that they were sensitive to the manufacturing process, whether it's pores or phases that come out during solidification. Theta is an important one, theta phase, aluminum copper phase. So we knew that, but we didn't until we then linked that back into the solidification models and the casting models and the heat treat models. We couldn't predict the effect of manufacturing history on those properties. But that's one of the key things that we were able to do, is have manufacturing history sensitive properties that drove the finite element analysis, durability analysis. So that was the real full sweep of virtual aluminum castings.
How many years did this all take?
Oh, all told, maybe a decade, in earnest. 5 or 6 years. I mean, we started some of the early ideas for a while, and then it built up. And finally, I tell you, there was a period of time where every aluminum product, cast aluminum powertrain product that was coming through would have a failure. So management knew this was a pain in the tush, right? It was costly. It took time. They never had field failures, but it was, during the product launch phases, something would break and we had to figure it out. So I was involved all the time in this failure analysis, figuring that out. But then when we sort of saw how we could pull all this together in this virtual aluminum casting idea, it was frankly an easy sell to management, because they knew this was a big problem for them. And so we basically expanded our team and brought it home. Yeah.
So it wasn't difficult to persuade people that we have all these wonderful computational models. I promise they'll work in the real world. Was that a barrier that you had to get through in terms of making the sale?
Actually, no, because we had done so much. As we developed this suite of tools, we were working hand in glove with people in manufacturing and product development and the CA analysts in both of those organizations. So they trusted us a lot. But we also did an immense amount of validation on everything we did, from separately cast samples that we would make in the lab to things from actual components. And by the time we finished this, so we had a room called the morgue. So everything that came through powertrain castings ended up in my lab, and we would analyze why it failed and so on and so forth. By the time this product launched, there was nothing in the morgue anymore. Wow. So, yeah.
Yeah, I'll have to tell my introduction to engineering students next semester, when we do some casting modeling projects, they don't know how good they have it. We can sit down in an afternoon, right? Throw together a CAD model, pour in some fluid, and be like, there's my region where the porosity is the highest. I guess I know what to change. And just, they don't question the magic of it, right?
Yeah.
But to have built that from essentially nothing is
Yeah.
an entirely different order of magnitude of work.
Yeah.
It's very interesting. So I'm guessing that this was the genesis of the integrated computational materials engineering endeavor.
Yeah.
How did that come about from this project?
Yeah, it's interesting. So, in science, there are often similar groups working independently that come up with the same idea. So an important one in fatigue is the Coffin-Manson law of low cycle fatigue. These two individuals were working independently, but they came up with the same law. Well, we were doing virtual aluminum castings, and I started talking about it at TMS meetings. And a good friend of mine he was one of my roommates at Carnegie Mellon, was a program manager at DARPA, Leo Christodoulou. And he and I were talking in the hall, having a beer or whatever. And he said they were doing this program they called Accelerated Insertion of Materials. And he described what they were doing with General Electric to do basically what we were doing with BAC. And so we said, we need to talk about this and see if this is really something that's more, the time is ripe for many people to be, maybe other people are doing this. And so one of the first things I said is we need to name it. Because, I knew it wasn't acceleration insertion of materials, because at Ford we used it somewhat for inserting new materials, but mostly we took standard 319 aluminum, but it cost us so much in these failures that it was really optimizing the product and the process from this existing material. I knew we couldn't call it virtual aluminum casting, so we just sort of noodled over that beer and a napkin, and we came up with the name Integrated Computational Materials Engineering. So
that's great. It just rolls right off the tongue. But you alluded to something very important. When we teach freshmen engineering, this Engineering 100 class that, originally started at Carnegie Mellon, teaching freshman engineering, disguising engineering as an English course or the other way around.
Yeah.
We teach them the traditional engineering process, which is design, build, test, and repeat.
Yeah, right.
That's
right.
the way we've done engineering forever.
Yep.
And your ICME got rid of the repeat.
That's right. And that was that was one of the main drivers. That's what we needed to do, because it's this repeat where you don't really understand the properties or the residual stresses and when you launch that product, you test it and said, oops. And so you got to really quickly go back and fix it.
And I know you're not going to say this unless I explicitly ask you, but you ended up, first of all, it's really cool you got to work on something that actually showed up in the vehicle.
Yeah.
But more importantly, you saved them a lot of money.
Yeah.
Like hundreds of millions
of
billions
dollars.
Dollars.
Yeah.
And so your team won the Henry Ford Award. Is that correct?
That's correct. It's the highest honor. We actually won 2.
That's right.
One for sand and low pressure casting and one for high pressure die castings. Yeah. And that's, to achieve 1 is kind of a lifetime goal. To get 2 is just really.
And you've always told me about what a team effort this whole thing was.
Yeah.
And you had a great team there.
Had
and
a fabulous team.
Great job managing that team.
Well, thank you.
So we're going to come back to team dynamics
yeah,
later.
Thank you. Yeah.
But I think we want to keep following up, because I think I know what Tim's going to ask. But
Well, I was going to ask almost the same question, but just to have this on the record, because I tell my students things and they don't believe me. I'm their teacher. I want to appeal to a higher authority. So I'm always trying to motivate the importance of modeling as part of the engineering process. When you design, have a predictive model, have a theoretical framework that's going to help explain why you expect the things that you do. And part of that is understanding what you're doing, which I believe is valuable in its own right. But back to the bottom line question, I have to imagine it saves a lot of labor and dollars and energy as well. So is there kind of a ballpark number, maybe a percentage for how much savings is caused by having this sort of ICME process instead of a traditional, Edisonian break it till it works approach?
Yeah. So as a result of the conversation with Leo, we basically said we needed to do some surveying. And so we got the National Academies to launch a study, so a 2-year study on what so we had coined the term ICME, but then we let this panel, which I was on, with Teresa Pollack, really coin the name, sort of solidify the name, if you will. But as part of that study, we did benchmarking. We determined there were other places that were doing this, many other places that were doing it. They just weren't talking about it very much, so we had to sort of dig it out. And the ROI, if I remember correctly, was probably 5 to 10 to 1. So we invested probably $10 million of Ford money. And a lot of that was databasing. It was employees, but a lot of it was just databasing. And saved Ford. By the time I left Ford, the number was up around 120 million, and I'm sure I'm sure it's doubled since then. I mean, that was 15 years ago, and they still use these tools. The group is still existing. Now they're working on gigacastings, these huge die castings for structures, for structural components, underbodies and things. So, yeah.
Well, you've alluded that your time at Ford did eventually end, as all good things must. So you won some amazing prizes, saved $100 million, and you didn't retire. You're still working. Look at us. So how did you decide to make the move to professorship after all that?
Yeah, well, so I loved the work I did at Ford and the people I worked with. It was just endlessly fascinating. But at a certain point, I said, is there more to this? And one day I got a call from John Halloran, a faculty emeritus, professor emeritus, John Halloran, and said, we think we need to bulk up our metals. What would you think? And I said, oh, that's interesting. Let me think about that a little bit. And it took me about a nanosecond to say, let's talk more. Because I knew, to be honest, I'd had a wonderful career at Ford. I'd risen to a very nice level. But, there was the ICME thing in particular said there's maybe more to that in terms of sharing it with students. A part of ICME, what we talked about in our National Academy study was sharing data and open source data. So talking to people about sharing information more, that cultural thing. I loved what I did, but I was never a car guy per se. But I loved metals, and so coming to University of Michigan and really focusing on fundamentals. So all of those things. I think the other thing at that time, we sort of knew something was bubbling around that became the Materials Genome Initiative, the presidential initiative in 2011. And so I knew there was going to be big team type funding coming to universities. I just sensed that. I didn't know it, but I sensed it. And I said, I can be on the outside at Ford, or I can try to be on the inside at a place like Michigan. So all of those things sort of came together.
So when that transition happened, like you said, things were going on at GE, but of course GM noticed what you were doing. Mm-hmm. And then of course the Navy figured out what you were doing, probably because of Leo.
Yeah.
And so very soon NSF found out about all of this. And quickly, I'm not sure when, maybe it was after you got here, or I know you had something to do with it. It's pretty hard to get a big center grant for developing new materials without an ICME component to your proposal. It's almost a required thing now. When did that actually happen? Was that after you got here, or is that where you were starting to sense what a big thing this would be?
It was probably about the same time. It was all bubbling around there.
Right.
So our report came out in 2008. There was an NSF-sponsored report that came out in 2009-ish. So there's just a lot of conversations, that you heard about and heard about that. But I mean, actually, the PRISMS Center, which
Right.
when MGI launched, each agency had to have something. And Department of Energy, Basic Energy Science, started what they call a program on software innovation centers. And so we put together a team and bid on that, and we're lucky enough to be awarded one of the first, basically, MGI centers.
And that was the PRISMS.
The PRISMS Center, Predictive Integrated Structural Material Science.
Nice.
Yeah.
And so you started doing similar things, but I believe you did titanium. Is that or magnesium?
The magnesium. Yeah. Magnesium. So I've certainly done some titanium research, but the focus on the PRISM Center is on software, data repository, collaboration center, and the science is all around mechanical behavior and microstructural evolution of magnesium alloys. I mean, lightweighting is really obviously important for many industries. Certainly the auto industry is one, but magnesium alloys are really immature. So there's a lot of possibilities there, and it's a very complex system that a lot is still not known about. So, yeah.
So you mentioned lightweighting. If I go back to Ford for a minute, why aluminum in the engine block? Was that for lightweighting or was that for cost? Why did they choose to go to aluminum engine blocks?
Well, it certainly wasn't cost. It was a bit more expensive. Not a lot, but a bit. If I remember, it's probably 70 cents a pound. And don't quote me on these numbers. Cast iron, its competitor, was probably 35 cents a pound. But it's primarily lightweighting. Also thermal conductivity and heat capacity is another part of that too, because you've got to get the heat out. I mean, you've got all this heat that can really cause problems with melting or knocking or whatever. So there's still a few blocks around that are cast iron, but I think almost every cylinder head, there might be a couple of diesel, or there'll be probably some diesel cylinder heads that are still cast iron, but pretty much everything in passenger cars is cast aluminum blocks and heads.
So ICME really had a major impact on lightweighting of vehicles, and you continue that with the PRISM Center.
Yeah.
So that's a pretty impressive sustainability goal that you've met. And how much lighter does the engine block make the car? Do you know that?
Oh, yikes. I used to know that number well. But
Alan Taub would know that.
Yeah, Alan might
instantly.
know that, yeah.
But Alan was your boss at one point.
He was. Actually, when we started virtual aluminum castings, we'd been talking about this for a while, and it bubbled to a certain point. And, Alan came from GE. He was our manager for a while before he went out to the divisions and then eventually jumped ship and went to GM. But yeah, when we started virtual aluminum castings, he was a manager that was very supportive. So
that's great.
Yeah.
And now you're colleagues again.
And now we're colleagues again.
That's fantastic.
Well, here, I know Steve tried to get us away from the ferrous, non-ferrous culture war, but I want to get back to that. So once upon a time, in the good old days, cars were made out of steel, or so I'm told. And we have aluminum pickup trucks now, the aluminum F-150 and all of that. So can you give us maybe a little behind the scenes peek of what that story was like and if you had any involvement with it, the transitioning to aluminum bodies there?
Yeah, so I had a little bit, not as much because I was still really focused on powertrains. I had colleagues who were working the aluminum body side, but I worked a bit with them. So we had some cast aluminum shock towers, so we applied our tools to that. And I also, at that point, I was in charge of some CAE portfolio within the lab, and so I helped with what we call materials cards for some of the welds and things like that. But I certainly saw a lot of, was listening to a lot of the stories that my colleagues were coming back with, and it was really quite a phenomenal accomplishment and, a real gut check if you really believe in this. So the stories that came back from senior management about, okay, we're going to all hold hands and jump in the pool together, they did it, and it worked.
And what was the driving force for that? Was it trying to get better fuel economy? Or
Yeah, absolutely. It's weight and fuel economy, sustainability, absolutely. So the model went, if we have a lightweight vehicle, we can downsize the powertrain. And so instead of having a V6, maybe we have a I4 for fusion. For an F-150, instead of having a V8, maybe we get a V6. And so it was the fuel economy from that lighter weight or lower powertrain that improved the fuel economy. Yeah, but lightweighting was absolutely critical to make that.
And is there, again, maybe a rough number as far as weight savings translating into efficiency increases? Because I think when some people think about sustainability questions, it can come across as very all or nothing, right? We have to electrify the world.
Right.
And to think about all of the places where you can shave off percentages and percentages that add up to actually very large numbers, how does that game shake out in the automotive weight area?
Yeah, I used to know that number well. I don't today anymore. I got another Alan Taub number. It's been a while since I used that number. Add it to Alan's list. It's, what is it? It's, well, let's see. I really can't remember the exact number, but they're very well documented numbers. Yeah, the weight saved per fuel economy, mile per gallon saved. Yeah.
But the legacy of the virtual aluminum casting is continuing, as you mentioned. I mean, the CEO of Ford just went down to Kentucky and talked about a new Model T moment.
Yeah.
And it's all this gigacasting.
Yep.
Because he explained it as this whole new platform where they're going to reduce the number of parts by, 15%, some pretty large number, and actually think about what the workers need to do to assemble them to make it easier so they don't have to crawl inside.
Yeah.
And all of this is going to add efficiency to the manufacturing process. And that's all possible with aluminum now because of those tools you gave them. And I presume they're also thinking about magnesium at some point.
That could do, yeah. Yeah.
But they're not there yet. They're thinking of this.
Yeah, so these are die castings. So both alloys are quite, good alloys in die casting. So it's conceivable they would do that. With magnesium, you'd have to be sure and get the corrosion properties, the coatings and the metal interconnects and things. But magnesium, you can actually get thinner walls than you can with aluminum. So yeah, it's
much lighter.
And it's much lighter. It's much lighter. But it's interesting. So we've got a really cool project right now, basically working using ICME tools with the Ford team to develop, they call it unicasting now, alloys, unicasting, these enormous castings, but that are, so typically these alloys, so let me back up. Cast aluminum powertrains are all secondary aluminum. That means they're 100% recycled.
Right.
The body castings have always been thought to require primary metal. So it's very, it's raw, it's pure material that's gone through the processing route, Hall, Perot, cells, et cetera. So it's very energy intensive and costly and emissions, CO2 heavy, if you will. And so, but with these unicastings, they want to have alloys that can have a high recycled content in them. And so that's one of the things we're developing an alloy right now with Ford and some other colleagues here at Ford, at Michigan, to develop alloys that are very unique to Ford, but also have the ability to have high recycled content.
Now, is that, I saw in the news that you, Alan, and Ashwin Shahani are working with a Danish company?
Norwegian.
Norwegian.
Norsk Hydro. Yeah.
Norwegian, to find a way to process recycled aluminum with zero carbon footprint. Very similar to what Jim Yurko did for Apple.
Yeah.
Can you talk about any of that? Or
Sure. Yeah, no, that's just popped a few weeks ago, and we're very proud of that and very excited by it. Frankly, it's a 5-year, $2.5 million. So there's 3 different projects. So Alan and Ashwin have projects around basically ingot casting to try to refine the structures, but get rid of or modify. There's iron is a really important impurity that comes along. If you're in secondary, so we just dealt with that in our cast aluminums, but with an extrusion. So Hydro is a big extruder, probably maybe the world's largest aluminum extruder. They worry about that, but there's also this product of recycled aluminum, which is called Twitch, brings along not only iron, but also higher levels of copper and silicon and zinc than they might normally want in their product. Because, wrought aluminum alloys, there's probably, 10,000 unique alloys, and each one is crafted very carefully. And so then you throw in this Twitch, the recycled content, and suddenly, all bets are off. You have to really figure out how to manage that. And so that's one of the projects we've got going.
But your role in this, I presume, is to use all your toolkit from PRISMS to do the predictive parts.
Yeah, well, we'll use PRISMS, certainly, but not everything can be predicted from models yet. So there's important parts of this program that will be empirical. That's an important part of ICME. So ICME is the capture of materials information in computational tools, but it doesn't necessarily mean that it's all physics-based. Some of it has to be empirical, and we're still that way. So we'll do a lot of experiments around this. Cool. Yeah.
I'm very much living my teaching of MSE 360 as you're talking about this, because in our junior lab class, the students are doing aluminum alloy design.
Yeah.
And as you're just talking about these other elements showing up and the importance of iron in the material stream, and every semester this happens is we'll be doing some SEM and the students will be looking in backscatter maybe, and they see something bright and they say, "What's that?" I'm like, "You tell me what that is. I'm not going to tell you what."
There you go.
And it's always iron, or some sort of iron manganese complex, things like that. And then they say, "Well, that's not supposed to be there. I didn't ask if it was supposed to be there. I asked if it is there." So is there, I don't know, a story or a piece of advice or just anything that is about why aluminum is still an exciting and important material to study, even in the 21st century? You've said yourself it's far from solved, but maybe what does the future of aluminum look like?
Well, very bright. I mean, lightweighting is, going to continue to be important for a very long time, maybe
Even
forever. For electric vehicles, it's a very important enabler, right? So having requiring less battery by having lighter weight vehicles is an important need. Yeah.
Yeah, I was shocked. I bought an EV recently, and the battery itself is 4,000 pounds. So my little vehicle is 5,000 pounds. It's really heavy, and I actually have to worry about some bridges around here to go over.
Wow.
And so, electric cars are very heavy. So they really need to worry about that. And of course, there's a lot of steel in my car.
Yeah.
You need that because that's a lot of weight.
Yeah.
But it's great in the snow because it's all down really low to the ground.
Good traction.
Yeah.
Low CG.
Right. So back to roads and things like that. You've been is it a trustee? Is that what they call it?
Ann Arbor Township trustee, right.
And I know you've learned an awful lot about gravel pits and
yes.
and roads and infrastructure for charging electric vehicles. How has that been as a sort of parallel career for you? Because you've been doing this for a while, right?
Yeah. Well, since 1996, I've been on the board, and for that planning commission. So it's quite different. I can use our scientific and analytical abilities to help think about all kinds of things, budgets and problems that we have to solve. So but I tell you, it's very rewarding to work with a team. We haven't talked enough about teamwork yet. So we have this awesome team of other board members. We've had this for that entire time. It's come and gone with different people, but it works really well together as a team. So working together as a team and accomplishing things, in this case for the residents of Ann Arbor Township, has got a real sense of accomplishment. Yeah.
That's awesome.
I have two questions coming off of that. The first is, just in your life outside of work, what was the time when your materials knowledge swooped in to save the day? The unexpected, I'm really glad I know about materials for this particular moment. So I was buying tires for my car the other day, and the sales guy was trying to sell something to someone. And out of the corner of my awareness, I hear him saying, "You can't possibly believe that. The glass transition temperature of this rubber is blah, 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 and there's no way it would work in the..." So did you ever have one of those moments?
Oh, I'm trying. I don't. Not one doesn't jump to mind. So a couple of them happened, failures. So we had Cutco scissors that failed on my sister, or my wife. She was cutting something, and the blade fell apart. Imagine scissor blades falling apart. And so I looked at the fracture surface and got out my 10x loop, and I sort of said, I'm not really sure what this is about. So that's become 2 projects in my failure analysis class. And I think they're going to figure it out this semester.
Okay, good. Well, let us know for the future what the solution to that particular problem is. And then you mentioned, of course, the working in teams to accomplish things.
Yeah.
And this translates both into the lab and outside of it as well.
Yeah.
So let's move into talking about teamwork for a little bit. When you're teaching, tell us about the classes that you teach and how teamwork is an important part of that.
Yeah. So early on, I decided that I would like to have something involving teams in all my classes, but also something involving ICME. So they teach both concepts. And so I formulated a team project around MATLAB codes to build a model around anything they were interested in. This team of 4 or 5 students would develop models, which weren't necessarily physics-based. They could be data-based, or at least parts of them, and then express that in a MATLAB code. So I got the opportunity to talk about teams, teach a little teamwork 101, and then ICME at the same time. So yeah, I've always valued teamwork, but especially since my Ford days, understood the importance of teamwork, and so I like being able to reinforce that to our students. So,
have you had any students come back after they graduate and say, "Oh, I'm so glad that we learned more about the importance of working in teams because do you get any of those stories?"
Occasionally, yeah. Or ICME. I've had people come back and said, "Wow, we learned about ICME, and I went on this job interview, and somebody said that word, and I knew what it was." So yeah.
Yeah, I feel like that's actually one of the best parts of what we get to do as teachers is when the students come back and say, "That thing you taught me was actually useful."
Yeah.
It feels great.
Yeah.
So how do you teach students how to be good team members?
Well, so just try to express the important factors of interpersonal relationships around a team, building trust, respecting each other, communicating, setting goals, meeting those goals. Yeah.
So you don't invoke these are the 10 things you need to have a good team. I mean, I've seen a lot of the literature, and I look at it and I'm a little put off by it because it's really not that difficult.
Yeah.
That's what you just said.
Yeah.
And I saw this great article that Google was trying to figure out why some teams work and other teams don't work. And after 5 years of using all these methods that didn't work, they finally went in and just watched. And there were only 2 things that mattered at Google. Did everyone on the team get an equal chance to talk?
Yeah, and very important.
And did mutual respect for each other develop on the team?
Yeah.
That was it.
Yeah. Those are
And those are important.
Yeah, absolutely.
Did you do any kind of assessment of team skills?
Well, so part of I use a program called CAPME to do to establish the team, sort of get the right balance of different things, but then also to do peer evaluations.
Right.
And that's that feedback is important. Generally, everybody does their part, and the teams are quite good. But occasionally, it doesn't work, and the message gets back very clearly in the grade, if nothing else. And as part of that, I also say, let's go back and periodically assess how your team is doing. So in some of the classes, I would have an interim peer review, and then we would assess how the team was doing, and is there a possibility for improving, so they can provide feedback.
Yeah, I use that tool as well. And I really like the anonymous comments that the students can make about each other, because you release them, and it can be brutal. It can be tough for a student to hear, but it's really important to hear about it. And one last thing on teams. I've seen people at CRLT have suggested the best way to make teams is random. And I just random. Nobody makes, in industry, you never make a team at random.
Right.
That's carefully thought about, right?
Yeah.
You know,
Yeah.
and you can't always throw your A team on all projects because there's only so many of them.
Yep.
So you have to use your resources as wide. You know, that's what a good manager does, is form teams that will be successful, but also be able to cover all of your jobs.
Yeah.
Is that
Well,
correct?
yeah. I sort of I take CAPME and give them sort of criteria, and they do a pretty good job of that. So I want distributions of GPAs. I mean, not everybody is the A student,
Right.
right? But everybody has something valuable to contribute, and that's part of the whole teamwork thing. So that's part of it. Diversity is really, really important, but also I learned this the hard way because at one point just wanted to make sure that every person had this X minority or whatever, or female. And then I realized, somebody taught me, people need allies.
Yeah.
And so
You can't strand
you can't
somebody.
strand somebody. So
Right.
that's an important thing for us
Right.
to always keep in mind. If there's somebody is in a minority, and so women, for example, in engineering are a minority. So it's important for everybody to understand that, but it's so important for them to have alloys on their teams.
That's right.
Yeah.
So I actually have one question in my team builder things that started at IBM. It's the 5 hats methodology. And it was streamlined by a professor at the Air Force Academy, a guy named Jensen, I think. And he turned it into 4 hats by combining, it was 6 hats and it got down to 4 hats. But it's basically like a Myers-Briggs thing.
Okay. Yes.
So it's
yes,
a bunch
yes.
of statements that I ask students, you know, are you an algorithmic thinker? Are you an organizer? Are you an out-of-the-box creative person? And I find that kind of, because people self-choose, and then I mix those because you want a diversity of different kinds of people on a team. But I always think about the Air Force Academy when I give you
Yeah.
questions.
So I have a different one. There's a book by Parker. I can't remember the title, but he has a little quiz on basically having people put themselves, by answering this quiz, into 4 different categories. I don't use that for team formation, but I ask them to all expose that to their teammates so they all understand people are motivated by different things.
Right.
And we always ascribe a motivation, right? Why did you say that? And I think I know why you said that. And I'm probably 50% right? Or maybe 20%, I don't know. But it's making sure that people really think about, well, I shouldn't ascribe a motivation because these people all have different factors in their lives that drive them to do different things differently than I might.
Right.
So.
Yeah, one of the things that I do in my freshman class is exactly that unpacking of essentially what's the reason you're here, in the sense of asking the students, what are your personal values and why did they inform your decision to become an engineering student? And we see a lot of different responses. And for the students to realize that there are even many reasons why one might want to be an engineer is something that many of them have never thought about before.
Yeah.
I am curious, because you have so much industry experience as well, is there something that you find is different between the sort of team environment in a classroom versus the team environment in working on an industry project? And is that something that we can communicate to our students in some way about what school is not preparing them for when they leave school, if that makes sense?
Yeah, I don't know. I've never thought about it in the context of, are there really substantial differences? I'm not sure that there are. I mean, the stakes in industry are obviously real, but the stakes here can be real in terms of grades and things like that. So, yeah, I don't know. Maybe the time that you have to solve a problem, is different. I mean, with virtual aluminum castings, we had 5 years, so we could have much longer to let things gel. Here you have a semester at best.
Yeah, so I do find that the artificially enforced time scale of all the things that we do here just drives some emergent dynamics of the team that can't be helped, unfortunately.
Yeah.
Well, what do you think?
I have one more question. So I know that you like to ski a lot.
Yeah.
And have you ever thought of starting a company that made cast magnesium skis. Would that help with skiing being really lightweight?
Cast magnesium skis would be a terrible idea.
They would crack.
Well, they would crack. They don't have the right stiffness. It's all kinds of. They'd be lightweight, but
So what are skis made out of these days?
a lot of them are made out of polymer composites.
Okay.
Probably most of them. Few that are made out of wood cores.
But no metals.
Not
the
too
edges.
that well. Their edges are obviously the metal. Some of them may have little sheets of metal interplied in some of them, I think, but I don't think that's real dampening type things. But plus, I was in industry for a long time, and I don't need to be an entrepreneur. I'd rather study something about metallurgy than try to be an entrepreneur.
Well, I think it's awesome that you're putting ICME projects into all of your teams as well as doing the teamwork. It's funny, I've done a lot with team-based teaching at Michigan, and I've tried to get as many colleagues as possible excited about that because it's so much fun to do team-based teaching. And you're like the only one in the department that's actually talked to me about it, and you do it. So we're like the only two.
There you go.
Oh, but that's a lab course is different.
I know.
Do you do it in your math course?
Some. Not
Okay.
as much as I'd like.
Yeah.
I need to
So-
learn from the
A MATLAB code, do
yeah.
that. Do a team-based MATLAB. And, people have different skills. You've got one student that's really great with the GUI, and one gal knows the math, and one person knows the physics, and
But GUIs are easy now with vibe coding.
Oh, is that
We'll
what they
just
say?
have AI do that part. But maybe you should put a ICME project into your math course because I think that would be a great project.
And I'm
Yeah.
always, I teach guest lectures on ICME in several courses. I'm always happy to do that or give people my slides or whatever.
Right. Well, we
That's
are
awesome.
getting to the point in the semester where it's really known of the students we have this term what their different strengths are. And I always think about the idea of for a final project, now that I know the students, very intentionally building teams to have those complementary strengths. And like you were saying, there are some students I have who are better at coding. There are some students I have who are better at the sort of theory of the math.
Yeah.
If I could pair those pairs together, they could really accomplish some impressive work, I bet.
Yeah.
So
yeah.
I'll have to talk to you about
Yeah.
implementing that.
Yeah, happy to.
Well, how long have we been going? I think.
Almost an hour.
Yeah, so I guess we probably should shut up. So thank you so much for being here. We really appreciate it.
It's my
We
pleasure.
always give our guests one last chance to pitch anything they want if they're interested, to talk about something we didn't talk about that you'd like our listeners to hear.
And who are your listeners?
Other materials educators, materials students, practitioners of materials, high school students who might be interested in materials, and their parents, so they actually learn how cool material science is, so they can help encourage their kids.
Yeah. Well,
do it in
so maybe
materials.
I'll direct it more at the students. I think materials is a great career. It's been something that I've been fascinated for many, many decades, and it's never gotten old. It's always a need. But the most important thing when you're, especially in undergraduate days, is to find the things that you like and the things that you don't like. And if you get in and you like metallurgy as I did, then it's the number of days you work is limited. You're always sort of having fun. Similarly, if you find things you don't like, well, just check that off the list and move on. So it's not for everything. Not materials isn't for everyone, but it certainly is a wonderful career. So.
Yep.
There it is.
All right. Well, thank you very much. And thank you all out there for listening to us. And by the way, we should have mentioned this. We have a new YouTube channel. So if you just search in YouTube undercooled.materials.podcast or just undercooled and materials, you'll find our podcast where we arrange all of the videos in one simple place. We have some nice playlists which will help organize them into things that are pedagogy, things that are discussions with faculty members, etc. So I hope you like it. So please take a look at that, and we'll see you next time. See you later.
Cool. Thank you.